Hello, today I will talk about Agile generation of Cloud API bindings with Haskell. This is joint work with Vitor Vitali Barozzi and Gabriel Araujo. So the problem that we have is that we want to use multiple cloud services, right? They have ad hoc REST APIs, usually documented in HTML. And sometimes the partial bindings in JavaScript, in Python, in Perl, random languages, but most languages are not supported. And this leads to the situation where when we want to deploy multiple services using these multiple cloud services, so we need to deploy application basically using multiple cloud services like Mailgun, Cloudflare, Amazon S3 together with Amazon Lambda. We see the tech stack inertia. Basically, we would be obliged to use the lowest common denominator language that is common for these services, and sometimes use multiple languages to deploy using different SDKs, right? Because they usually support only few SDK languages. And sometimes even there is a fixed container where deployment works, or you need to deploy the fixed container. There is also support for OpenAPI that allows you to generate the bindings from common specification for multiple languages, but it's generally poorly supported by the vendors, if at all. And OpenAPI specifications that you can get are often partial and partially incompatible with the latest spec of the OpenAPI or with any spec. So our goal would be the tech stack agility. So we want to program our deployment and our service in any language, in particular in our favorite language Haskell, and with any library stack. So we may want to support any library in any environment like Alpine Linux, Ubuntu, or Red Hat, or Nix, and allow fast replacement of different components. So we want to switch from using mail service from Mailgun to the mail service from SendGrid, right? And then to Amazon messaging service, so email service. That's important because sometimes you know that each of these vendors are best of breed in one certain particular domain, but not necessarily in others, right? There are big bundle vendors like AWS, but they will also never be the best in terms of features and support in every way, right? So you want to mix and match best of breed services and replace them at will. And you also want to combine best available microservices sometimes. From AWS, the same service, and from Google Cloud, for example, right? You want to deploy your services to different platforms, right? Not rely on one particular SDK version that is supported only on one platform. And you want to do it with low amount of code. Why? So because the requirement here is the agility, right? So to make a minimal change and get maximum effect, people have been advertising so-called no-code or low-code approaches, which is basically to configure certain things by a GUI, but then you don't have infrastructure as a code deployment, right? So you would like to configure it and then put the code that configures it. And this is the easiest with just making the same thing that you did by GUI by making a API call. But you don't want to to support library of entire binding to Mailgun, for example. You don't want it. You want something that will allow you to just support Mailgun with minimum effort, with no new code needed to be written for each particular service. So the solution would be the code generation of API and SDK bindings from HTML documentation, so directly from vendor documentation, without caring whether vendor supports our language or not, whether caring whether supports even know how to write open API specifications, and without waiting for vendor support in this way. We use per API scraper, then we output the common format, which we analyze in Haskell, and we also write the code generator in Haskell, which means that we have only the analyzer, common analyzer and common generator code to support, which is much less than the entire code that we generate for all APIs. This solution is retargetable to other languages because we really don't need to support the whole language syntax on the output. We just generate type declarations and methods for each API call, and the types to nicely construct the call parameters, right? So this is relatively easy. And the issues we have with this approach is that there are really multiple REST methods, call conventions, and type conversions. So for example, if you think about REST call, it can have different methods: get, post, put, delete, patch, right? When you think about parameter passing to the REST call, it's even worse, because in a single call you may have multiple ways of passing parameters. First, it may be in HTTP request path variable. The second, it may be URL and encoded query parameter, or it may be HTTP request header. Some of them are actually proprietary and very specific to the vendor. Sometimes it's HTTP cookie or authentication header, or it may be actually JSON that you need to parse or write for the request body or response. So there are many things like this. And in this request body, you may also need to do a type conversion from to JSON XML. And there are special strings that have special meaning. So for JSON, because this is the most popular format for request and response, we use JSON autotype, which allows us to automatically derive the type from the examples in the documentation, and the parser also, right? So overall, the implementation is quite complex and consists of these three stages. So first we do scraping in Python from crawling URLs to CSV. Then we do parsing, and we use both JSON parser and JSON autotype to derive the types and parsers for JSON objects. A parameter descriptor parser and HTTP request parser, and also use example parser, because sometimes it's documented how you use the call, so you can validate your idea of the calling conventions with, say, call stance, right? So shell script. And after we describe this call in single coherent description, we do code generation. That is targetable. Now we generate code in Haskell, and we will support other languages. So for example, this is code generated in Haskell with a nice link to the documentation of the API, and nice type that allows you to incrementally construct call parameters. The same for the response type. You can incrementally parse deconstruct the response type. It's also all validated, and it uses servant client types. So you have actually type for the endpoint of the call, so you can easily mock it, for example. And the limitations of this approach are that you have specialized components sometimes that you need to support by adding extra code, which is like custom HTTP transport in case of AWS chunked or Amazon chunked, or custom authentication methods in case of TransferWise. For example, you need to sign every request with the private key, right, instead of using, say, JSON web token. While this may be secure and good way to do it, it's non-standard, so you need to add extra code to support it. the other thing is that we do replicate bugs from documentation, so we rely on vendor for keeping documentation accurate. And there are fewer and fewer companies that do not provide REST documentation. They just provide language-specific SDK in, say, JavaScript or Java. For this, we would need a different approach, but it's still, the coverage is really, really good. Because the benefits is we have really thousands of API calls available within months. It's easily retargetable to other languages. It's easy to scale to new APIs, to add new APIs, but just scraping them, the documentation. And we no longer depend on vendors. It's really critical that we can do what we prioritize, right? Instead of waiting for somebody else somewhere to catch up with innovation. The interesting part is that compared to the API bindings that are supported by other methods, we really reduced the supported code base. Our code base is much smaller than, say, Amazon code base, even just generators in Amazon code base or Google, and definitely smaller than the code base of generating API calls, or say any API bindings for serious APIs in other languages like Bottle, right, in Python for AWS. We also offer a paid service from Mega.com, so even if a company stops functioning, we promise that we will provide some way for you to use this service in the future, maybe open source. But while you are waiting for our big open source release, you probably want to make similar data pipeline at home. So let's talk about this. How do we believe we can do it fast and accurate? So we have these principles that we use, which is basically prioritizing the quality and quantity of observations over fast iterations and continuous processes. Well, why we use all three, but still, quality of observation is the paramount for data. Working pipelines and aggregations instead of rigid schemas. So instead of schematizing everything and pre-specifying input and output, we basically make the pipeline work in such a way that it works always, and it aggregates and tells you what kind of errors are still there. We also prioritize informative feedback from analysis over the expectations of what should be on the output. And we use exploratory programming, so we basically reveal data in the process of analyzing it, of building the analysis to learn more and more about this data. I will show you the examples in the Haskell code. So let's start with a simple record. This is much smaller than the record that we use in our pipeline for the API bindings, but it will show you all the relevant things. So you have a description, which is a string and amount and a date, right? So different types. And the first rule is that you want to use standard data formats. So use from JSON to JSON, derive from JSON to JSON, from named record to named record. This is from Cassava for CSV records, and use them, right? So you can dump the input and output at every stage of the pipeline. It may be that in the initial stage of the pipeline, you only have some information, so you don't know what is the amount, for example, only have description. Then you would use maybe int to say that we don't know yet the amount, or you will use higher kind of data types that I will discuss later. And for now, make sure that you can always read and write the current data format. And which intermediate data formats to use? So you see the most popular ones are well supported by the tools for viewing and for classifying them and putting them into database. In particular, JSON is increasingly popular for complex objects. XML is still very popular for long-term migration and compatibility reasons. CSV grows in popularity because people realize that more and more data is tables. So you have a list of records that may be table of records. That's easier to read, right? And that's why we use CSV as a primary format. But if there is something that doesn't fit in a single CSV column, what we use, we just put the JSON object inside the CSV. And then we can browse it with spreadsheet software and see the overall statistics with pivot tables, say. So that's very important that you have standard data format, because it allows you to easily debug and browse at any stage of the pipeline. And now let's talk small, which is like really parsing a single record. Okay, start small. That's how you start the data pipeline. Try to enter the record into your data pipeline, right? So you have a list of columns, which are strings, and you make a record. But wait, sometimes you have an error, right? So the many people start by doing this by saying that when you parse a table, this is a list of records, a list of columns. You get maybe a record or maybe a list of records. Oh, too bad. Why is it the first mistake to make and it's so bad? Well, because when you give maybe, that means you give correct result, right? Or no information, which means you cannot debug the problem really if it's it may occur in many places, right? So what you want to really give is either a reason why there is an error or a record, right? And you go further. You can use these standard data formats to capture these error messages as additional columns, for example, right? So we have these standard field exports in Cassava, and you say that either you have a string, which is error message, or an object, and you convert it to name record. Then you can use Cassava generate, and you always are able to write both erroneous and normal records. So you say, now we would have either reason why we stopped and the record. That's better, but it's still not good enough. So maybe is a root of all evil and all opaque errors. But we want to more and more transparency, more and more information about how to debug this issue, right? So another example of this problem is that nothing and no information is evil, and filter does the same. So whenever you use filter function for the records, for a set of records, you silently discard a subset of records. That is bad either. So when you use either, you should use not filter, but partition either, and split records into two streams, like error stream and good data stream, right? And if you have any problems with the performance of partition either, you can use the only way that filter is morally justifiable, which is to implement partition either in a more efficient way for lazy partition either. But let's come back. So here we have an example where the compiler returns the message of why it happened that we had an error, and then it crashes. Did you ever see the head of empty list message? That's not very informative in a big program, right? And now think about parsing millions of records. Not really. That's bad. So you enrich the error message with location, and then more location, and then you start adding and adding on top of it. And that's the right approach, because certain things about the location, like file path, you can only learn at certain stage of processing, in certain moment that the code is nested. So you may want to use a so-called contravariant logging or logging profunctor, where the left parameter is error message and it's contravariant, and then you dump it and you convert it to richer and richer error message gradually at different stages of processing, while the right parameter of profunctor is a conventional result of the monad. So we have a data monad basically where you have a writer T, which contains a list of errors that can be consequentially enriched with the lmap function. And you have the result that is conventionally and the monad on top of which you process it, that allows you to access, for example, database or reference data. But sometimes it's a little bit more complex. So if you have a complex object like JSON objects that may be big, then you should always add the path to really point out where exactly error happens so you can find it quickly. And the right way to do it is to enrich your generically derived from JSON, for example, with the information about the in which fragment you have the error, some prepend failure. Each time that you go down in the data structure, say we go left or right, and this is where error happened, right? So we have this this path where each time we process something, we may return good data or we may return extra information for the error. That's a very important principle. If you go even further, then you get this error handling with either. And you may process a big collection. You still want to get better, because either one error or a record, that's not enough. For really big data sets, that's not enough. Assume 1 in 10,000 chance that you have a record failure, right? You are almost certain that you will process a 10 record file, but if you have million record file, you are almost certain that you will not succeed at the first time, and that means multiple iterations of running the analysis. When you run the analysis like this, that will be very slow. So what you want to do is to do what I told you previously. You have two paths, error path and data path, at each time in your pipeline, and you just say that these records that were erroneous, they don't disappear. You don't use filter. You don't let any data disappear. You just move them to the error path where they will be enriched with extra error information, right? So you, all the way down in the pipeline, you will go to show you more and more error information. All process the correct data. Never let it disappear. No information is lost. And that means also the correct records are not lost, because one error will not make you stop the analysis, right? You will just move this record into the error path. And then for even larger data sets, you can think about basically making a monolith that allows you to report the failures. Of course, I remind you, we don't use the monad here, right? So we have this pair of failures and successes, and you can basically make it monad writer, where failures are just to be appended to or converted as a profunctor with enriched information, but you don't lose them. And then when you have a lot of errors, like millions of errors or above, you stop using the monad writer. You may use map data combinator to make this switch. So basically map data is map the function that can possibly return the error, and if it for any list item it returns the error, you switch this item into the error path, or you keep it on the data path, right? Or the correct data path. And then you replace this write a monad with some logging monad that is basically contravariant logging usually, that immediately dumps the error into some file, and then you reread it to avoid the issue that you have so many errors that they block your garbage collection. So in a way, you can say that old school data pipelines tell you to basically look at the correct data path, make sure that it's all good data there, it's well validated, and then you dump the errors at each stage. And that's not what we do. That's not what we recommend. The new style of data pipelines is watertight. You never let any records disappear. If they leak because they have an error, they go into another path, into the other pipe, which is basically error pipe. And then they are enriched with additional debugging information when that is necessary, right? At which stage it happens, to which file it happens, to which line it happens, and so on. Also, you want to keep the error path to be used only in case of errors, because you don't really need to care about correct data being from this or the other line usually, unless you need to recover certain information. So we have two paths. One is for correct data to the output, and one is for the errors to the error dashboard that gives you overview of the pipeline and health of the data. So Navy SEALs say leave no man behind. Data SEALs say leave no record behind, ever. So this is an example of the data dashboard. It tells you not everything is complete, not everything is finished, right? What is passed, what is correctly processed, and how many calls there are in total. So we can assess the impact of each error. There is a similar dashboard that shows you how many errors of each types are there, like this one. That's the right approach, because this allows you to prioritize the most important errors and assess the impact of them. And you can do aggregation of errors easily if you have a list from write and monad that will basically group by certain prefix of error message and sort by this prefix. And that's already enough. That's already enough to start with, to get this kind of nice dashboard. And the correct aggregation gives you much better results. So you can sort by the different things, right? You can sort by the quality, you can sort by number of calls, and you immediately know what happens. And this is another way of viewing this, the pipeline where nothing is lost. When everything is watertight, you easily get to the situation when the losses in the data, input data, are small, but still it's at any point of time you can say how much each error or each problem is affecting the pipeline. And finally, the last technique that we use is that we also use the common record format as far as possible in the pipeline. It's like GHC core data, right? To do it, we use higher-kinded data types, which basically means that the record has a small argument, which is a functor. That is a representation functor that tells you how we represent the data inside. So if we have a valid record, then this functor will be identity. That's the same as the type that it takes as an argument. When it's unparsed record yet, so first you load the record and then you parse it, right? Elaborate load transform, not elaborate transform load, in a way. So then you use unparsed functor that gives you basically the string representation that is to be parsed later. And you can do similar things, but to add in additional information. You may want to listen to Simon's talk again about GHC and how they use these higher-kinded data types in GHC pipeline from Zurich 2019, I believe. And just to reiterate the principles that we use to make our watertight data pipelines, I remind you. And maybe there will be a book one day that you can read to make sure that it's like a handbook. First, just reminder of Agile core principles, but our data principles are different. So first, we prioritize the quality of observations over fast iterations and continuous processes. We use all of them, but first quality of observations. Then we work on pipelines and aggregations over schemas and specifications. Analysis feedback is much more important than expectation that you have, say, 90% data processed. It's really dashboard that tells you what happens. And don't think that you need a spec for data. Just reveal the data as you write the pipeline, because that means you have a good error handling that tells you what happens with the data really, and not what you think it should be happening. For example, number of observations is the most important. Each time you have an error path, you see so many error observations that will give you feedback. Standard data formats by dumping everything in CSV or JSON at any stage and reading it again to check that it's valid. You can tag records with warnings to also enhance this sorting into error path and data path and add additional categorization to your errors. Never discard records, right? No record left behind. Always tag them as errors instead. You have watertight pipelines because of that, so no record should be lost, and that gives you the error dashboards. Finally, I recommend assigning unique record ID for easy tracking, just like in cloud monitoring. Thank you very much.